So good afternoon, everybody. My name is Siegfried Rupprecht. My colleagues and I have been working on the CoExist project from the coordination side, and today is our final day, not in terms of the project, but it is the day for presenting to the public the results of our work. Our consortium of partners has worked very hard for 3 years on the topic of automation in the urban context. We have worked within Europe and also outside through a twinning arrangement with partners in the United States. And we are very happy to present to you today the results of our work. Obviously, we had planned a face-to-face meeting, but for the reasons that we are all aware, we have moved this, we have compressed the program into a 3-hour web event, which we are starting now, and there will be some satellite meetings tomorrow as well. So welcome on this sunny day. Please enjoy the 3 hours. Please participate and enjoy not talking about Corona, but talking about automation. So before we really get into the conference, I would like to ask my colleague Daniel one more time to very quickly explain to the people who have arrived late the functionality of our web conference. Daniel, can you continue?
Yes, thank you, Siegfried. Hello, everyone. So as I was mentioning before, for participants who had joined earlier, we have an instructive set of slides to show you the webinar functionalities. First of all, the way you can change audio connection. If you have any trouble with the computer audio, you can move to a phone call. There's a set of numbers for different countries, so please find that in your panel. You're muted by default, but you can raise your hands if you would like to get our attention, and we can unmute you so you can participate and pose a question to the speakers. There's also a question box where you can interact with us. You can post questions throughout the webinar, throughout the event, and we will be compiling them and putting them to the speakers, or also helping you with technical difficulties through this question box. We will use polls also to engage with you, as you've just tested a bit some minutes before. We're going to be doing this throughout the presentation, and we will have 3 to 5 minutes after each presentation to raise some of those questions that you've sent us for the panelists. The last aspect we would like to point out is that there's 4 different handouts which you can download directly from your panel. Here you can find the events program, some of the CoExist deliverables, and an instructive with these explanations on how to connect, how to change audio, how to raise questions, and so on. Thank you. And should we?
Thank you, Daniel.
Right. Yes, thank you.
Marie, are you ready now for the poll?
Yes, I am ready, and I hope it works. So let me show you the first official poll. And please, you can just try and hit the screen that you're seeing to whatever fits. And I'll close this poll in a couple of seconds, so please be quick. I will wait 10 more seconds, so we'll be closing the poll 3, 2, 1 now.
Okay.
So let me share the results right away. We got over 80% participation, so that's pretty great. And most people are joining us from Europe, so you're probably in a similar time zone as we are. And then also we have participants from North America and even from Asia or Australia, so welcome.
Okay, great. Thank you very much. So let's continue with the program. Wolfram, can you move on?
Yes.
Okay, so just to give you a little overview of our program, on this first day, the focus will be on automation-ready transport modeling and infrastructure assessment in the first part. So this will be like for 1.5 hours almost. And the second part then is about results from the impact assessment of use cases. And that will be finishing around 5 o'clock this afternoon. And we will try as much as we can to stick to the time scale that is given on the agenda, so that people can dial in, and we hope not, but if needed, also leave for some part which is less interesting for them. So without further ado, I really would like to then continue with the program, but before that, I would like to Wolfram, please continue. I would like to give you a little outlook on what is happening tomorrow. Tomorrow is the focus on the cities. There will be presentations from our partner cities, Milton Keynes, Stuttgart, Gothenburg, and Helmond, and from Polis, but this is really for tomorrow. Just to put a face to the people working in the background, these are the people from the Ruprecht team. So please, if you have a question, Daniel will be looking after that, or if you have a technology question, ask Marie or Wolfram. Please ask your questions in the chat, and they will be looking at what is coming in and trying to help you. If you have a technical question, please download the document IT Instructive, where there is also an emergency telephone number which you can call and which will connect you with Marie. Okay, so this is the introduction. I would like to hear is Georgios Saros. Georgios, are you here? Can you please raise your hand?
Can you hear me? I'm here.
Oh, you're here. Oh, perfect. Okay. Georgios Saros is from the INEA, from the Agency of the European Commission, who is managing our project, and Georgios is our project officer. So over to you, Georgios.
Thank you very much, Siegfried, first of all, for this invitation. And of course, I understand that this is quite a difficult situation for all of us. But as you said, I mean, let's look the positive point. We're all at home with families, but also we can work from home. And here I will really welcome you from a sunny day in Brussels. So I would like to thank you for the organization of this remote, let's say, conference, a virtual conference, where actually you adapted very well to change from the physical conference to a remote conference. It's a pity that our colleagues in the UK, where you had organized the conference, unfortunately, we cannot join the UK, but at least now we are all online in order to participate and to see the results that CoExist implemented and developed during the last 3 years. As you already know, I mean, the stepwise introduction of automated vehicles in the traffic, on the road, will of course face a transition period where actually the coexistence of conventional and highly automated vehicles will have to be managed in order to ensure an uninterrupted level of safety and efficiency. Of course, for this, in order to achieve this one, different actors play their own role. Of course, as you can understand, public authorities, road operators play their own road transport road infrastructure play their own role. And of course, I'm really happy that I see in the agenda that a lot of time is dedicated on this aspect. I mean, I can actually distinguish some of the deliverables, final deliverables of CoExist that I would really encourage you, I mean, Siegfried and your team, Daniel and Wolfgang, to actually make them publicly available also to the audience, which is about the action plan for road authorities, guidelines on how to become an AV-ready road authority, and of course, recommendation on road infrastructure design. It's really important. I mean, this is a topic where CoExist is funded by EU funds. And of course, we have 2 more projects funded under the same topic. But on top of that, there are also additional projects funded from a CDR, where actually I really encourage you to discuss your outcomes with the other projects in order to somehow converge your opinion into one direction, which will be very helpful for the Commission and for the second platform activities which are now happening at the Commission level. Another point that I would like to stress to my quick welcome to you is also that CoExist was one of the good examples that we had collaboration with the US. So as you know, the Commission and the US DOT had an agreement in order to twin projects from Europe and the US. So CoExist and the project from the US have agreed, and they have made a twinning agreement. And I'm really happy that, of course, representatives from US are now online, and also they will participate and they will present results in this virtual conference. So I'm really happy that this collaboration went well. And of course, as I always say to all of my projects, is that the real actually development, the real implementation starts now, after the end date of the project. I mean, how now it is important to build up on the results that you have already achieved, and how you can further exploit these results to the next steps. This is also important for us because now, as you know, we are somehow shape the new framework program, the Horizon Europe. So it is really important for us to have your feedback, your recommendation, your somehow some hints that we can actually take into consideration for the structure of the new framework program. I think that's all from my side. I don't want to go into much details. Just for your information, at least for the European partners and for European colleagues and participants of this call, due to the current situation, I'm sure that that you are aware of, but I just want to highlight that some call deadlines have been postponed, at least for these calls that they had the deadline until April 15 of 2020. So please be aware. I mean, please visit Commission or INEA website on a regular basis to be informed if also other calls will be postponed as well. Because as you know, we have now 2 topics on automated road transport with a deadline on April 21st. So now we are in a very critical period and a situation where maybe, I don't know, we don't have further information on that. But please keep in mind and keep you informed through our websites. Once again, I would like to thank Siegfried and your team, Daniel, Wolfgang, for your effort that you have made so far to organize this workshop. And also, please be open with the participants and share the documents, at least the ones that are publicly available, to your participants in order to receive maybe additional feedback to your texts. Thank you again for this conference, and I really wish you a fruitful discussion today and tomorrow.
Many thanks, Georgios, for your encouraging words. So, in order to move on quickly, can I ask Daniel to give us a very quick introduction of the CoExist project? And then it'll be Johan. Sorry, Johan. We still have a little introduction for our project to have.
Yes, hi, thank you, Siegfried. So for a very quick intro on CoExist, first of all, I wanted to mention, as Georgios was highlighting, that we will send with a follow-up email a week from now links to deliverables and different products from CoExist. So please be on the lookout for that. So CoExist is a project which receives funds funded by the European Union's Horizon 2020 Research and Innovation Program. It started in May 2017 and it's going until April 2020, so we have about a month to go. And its strategic aim is to bridge the gap to support public authorities in this transition between automated vehicles and transportation and infrastructure planning. How can we consider them adequately, efficiently in planning activities, and to strengthen the capacities of urban and road authorities and cities to effectively plan for the deployment of AVs. And to do so, we've defined automation readiness as the goal towards which CoExist aims for, and this is reaching automation readiness means reaching a high level of capacities, a good capability to make structured and decision about the deployment of connected and automated vehicles. CoExist understands that automation-ready transport and infrastructure planning in cities is a key precondition for fulfilling the promises of CABs to reduce road space demand, to improve traffic efficiency, and to improve safety. And to do so, CoExist has addressed this in 3 key steps. The first of which is automation-ready transport modeling. CoExist has developed validated extensions of existing microscopic traffic flow simulations with PTV VISM software and macroscopic traffic transport modeling with PTV VISM software tools and scripts. These tools include different types of CAVs and different automation levels into the modeling. The next one is automation-ready road infrastructure, and to assess infrastructure, CoExist has developed tools and a methodological framework to assess the impacts of CAVs in urban mobility and road infrastructure, and has worked together with road authorities to reach automation readiness. CoExist has elaborated 8 strategically selected use cases in 4 local authorities. These are Gothenburg, Helmond, Stuttgart, and Milton Keynes, and use them to evaluate CoExist tools and assess the impacts of CAVs and the requirements of infrastructure in the automation transition. This is what I wanted to share with you and what you will gonna listen to in the next presentations. Thank you. Back to you, Siegfried.
Okay. Thank you, Daniel. We are already a little bit late, so quickly over to Johan Alstom. Johan is from the VTI, the Swedish National Road and Transport Research Institute, where he's the senior research leader. So over to Johan, please.
Thank you, Siegfried. Yes, and I will present an overview of the impact assessment approach we have been developing and using in CoExist for the use cases. I would like to start with giving you some ideas on what the challenges for doing traffic modeling of automated vehicles is, and then I will focus on how we have been approaching this to deal with the heterogeneity variations in driving behavior among automated vehicles, the uncertainties related to the evolution and deployment of automated vehicles, and then how we have developed and applied the assessment for different use cases, and how we have showed a range of results. So how to model automated vehicles and traffic models. The first question is, of course, what is an automated vehicle? It's not obvious. We need to know how it behaves. Are all automated vehicles behaving the same or different situations? These are questions that need to be answered in some way. Someone is switching my slides without I'm doing it. It's interesting. So why is that happening?
Sorry,
okay.
Let me check.
Yeah. These are questions that you need to be able to answer in order to do modeling. I will continue from this. The SAE levels here that we have seen several of us is giving some information, but it's mainly giving information on to what extent the vehicle can drive itself and where it can drive itself and who is responsible for the drive. But it doesn't say how the driving behavior will vary between the different levels or within a level. So in CoExist, the focus has been on high automation. That was in the call text. So we have been focusing on when there's some automated driving system that's responsible for the vehicle operation. We have not considered the transition between manual and automated driving. So either vehicles are manual driven or they are driven by an automated driving system. That means when they are in automated mode, they comply with the speed limit and other road regulations. So challenges for modeling is that we have limited data on the first generation automated vehicles. There are some, but they're commonly properties of the OEMs. We have no data on how the AVs will behave in the future. And as Georgios was into, the transition will probably be rather long, or there will be a transition period. And there will be large uncertainties with respect to, for example, driving behavior of automated vehicles, the deployment and evolution of AV technology and penetration rates, and also on how other road users will behave in response to automated vehicles, or if there will be behavioral adaptation with respect to travel time, perception, and so on. So I think it's already now time for the first poll to engage you. So which uncertain factors do you think is most uncertain?
Yes.
Marie, can you?
So let me show you the poll. As we trained before, you should be able to select one of the options by just clicking really easily on the screen. And I will close this in the next 20 seconds, so be quick. Select one of the options. For now, we have over 30% participation, which is great. Just keep going. And I leave it open for a couple more seconds so that we reach maybe around 80% participation, 10% left. Take your chance. And I will close it now. 3, 2, 1. And I'll share the results right away as well. So most people said that the behavior of other road users in response to AVs would be the biggest uncertainty factor, closely followed by the evolution of AV technology and penetration rates. And then we have also voters for 14% for driving behavior of AVs, and as well as traveler behavior adaptation, 13%.
So interesting to see, and I think independently on which uncertainty is most important that you think, all of them I think are important, we need to deal with them in the traffic modeling and an assessment on traffic impacts of automation. So that's commonly we do with scenarios with consistent assumptions. What approach in CoExist has been to do conceptual modeling of AV capabilities with respect to perception, anticipation, driving logics, rather than modeling of detailed specific AV functions as ACCs or so. So we focus on how and where AVs can operate safely, and we don't model the technology that make that possible in detail. And we have conducted this kind of sensitivity analysis. So this has been done by a hierarchical structure. So we have created something called AV class in our framework and something called driving logics. So we look into 3 different AV class: basic, intermediate, and advanced. And we have 4 different driving logics: rail safe, cautious, normal, and all-knowing. And I will explain those in detail in the coming slides. So the idea is that we have divided automated vehicles during this transition stage into 3 different classes, where we have the basic, which can be self-driving only in less complex traffic environments, one directional with physical separations, active modes; intermediate, that can be self-driving structured traffic; and advanced, that can manage most environments, but not maybe all of them. And all of them need to prioritize safety, of course, but the more advanced one can drive safely, but in a more offensively or confident way. And as I said, all need to comply with the road regulations. The driving logics, there are 4 of them. The first one we call rail safe, which is similar to what we see in the automated minibuses tested around the world. So it's follow a predefined path. It cannot do lane change. You can only follow this path. It follows also a brick wall stop distance criteria, meaning that if a vehicle or a road user in front would suddenly turn into a brick wall, then it has to be able to stop in a safe way without collision. So it's kind of a switch principle. If anything is in collision course, then it will slow down and stop. The second one we call cautious, which also operate according to the brick wall stop distance, but don't have to follow a predefined path. So it could do lane changing, but the brick wall stop distance is required in following, lane changing, merging, and so on, which will require quite large gaps, and the vehicle needs to slow down every time the sensor could have blind angles. Third one is called normal, which is similar to human driver, but with augmented or diminished perception due to sensors. So parallel sensing is possible, but maybe only seeing one vehicle ahead and don't have the anticipation possibilities of an experienced driver. The last one, called all-knowing, is looking very far away in time, probably, at least to my view, which could be perfect perception and prediction of the behavior of other road users. So it could drive very offensive, but still being safe. So it could be, as today, it would be felt like a very aggressive driver. But the idea is that it's still safe. So we have, okay, one more. We have combined these AV classes and the driving logics to describe where different types of automated vehicle could drive, in which road environments, which driving context, which operational design domains, and using which driving logic. So our assumptions is that the first kind of automated vehicle, basic, could drive only one directional traffic, both ways and material, but have to be very cautious. But human driving is really required in the urban and street and shared space kind of environment. And the more advanced AV, the more advanced driving logics can be used, and more road environment, more and more complex road environment can be handled. The transition period will probably be long, so and it's very difficult to say what will happen at 30% penetration rate of automated vehicles, because you don't know how the mix would be between different kinds of automated vehicles. We don't know if the transition will be linear or not. We have divided the transition period into 3 stages: introductory, established, and prevalent, which are characterized by the market penetration rate. and also the mix and the deployment. So introduction stage have low penetration rates. Conventional drive is the majority. Established is when we go from conventional vehicles, manual driven vehicles being the majority, to automated vehicles being majority, and prevalent is where we have a high share of automated vehicles. We think also that it's reasonable to assume that for the introductory stage, there are mainly the lower level, less advanced types of automated vehicles. And as we go to the established stage, we start to get a larger mix. And then we can get more and more advanced AVs with high penetration rates. This is, of course, assumptions, but we have built a framework where the user itself can choose what combinations of fix are most reasonable for the different mixes. So, for example, we ask you now a poll on which you think is the most, which mix of basic, intermediate, and advanced AVs do you think is most probable in the established stage?
So you can vote on that now, really easily clicking your screen again. We already have more than almost 20% participation. You still have a little bit of time left to give us your opinion. What you think is most likely or most probable in this stage. I'll just give you 10 more seconds to respond. So just click on the screen and then you can easily submit your answer. Now close the poll in 3, 2, 1. And also share the results really quickly. So almost 40% seem to think that the mix will be 20% basic, 60% intermediate, and 20% advanced. And then the rest is fairly distributed, but it seems to be a high uncertainty as well. Johan, maybe you can take conclusions from that.
Yeah, I don't draw any conclusions more than that it's uncertain and different persons will do different assumptions. And again, we need them to vary and look on several different combinations. So now we'll see. Okay, sorry. There's a delay in the switching. So in order to assess the traffic impact of automation, we have been looking into a definition of automation-ready infrastructure. That's an infrastructure that if we add automated vehicles, current conventional vehicles and active modes should not have a significant decline in performance. We have been looking to that in terms of that we looked into metrics as delay, travel time, space efficiency for a certain combinations of penetration rate and mix of automated vehicles, and relative improvement of that compared to a case without any AVs. So, for example, we can have look on certain factors as penetration rates, AV mix, and different demand levels. In this example here, we have two different AV mixes for established stage, and we have the red ones here being the different penetration rates considered. This is again assumptions that can be varied in the framework. And in order to present results, we have been presenting the results including the uncertainty. So we present results per stage. So for the introductory stage, the established stage, and the prevalent stage. We have been presenting the median results for all the different combinations of uncertainty factor, penetration rate, mixes, demand levels, but we also show the mean and max values. So these kind of graphs you will see later on for the use cases. And here is relative improvements. So a positive value here is an improvement, and a negative value is a decline. For the safety part, we've been using a quality safety assessment because we don't believe it's possible to do safety assessment based on the output from the microscopic simulation models, especially not with automated vehicles. So we have been looking for the driving functions and different types of accidents for different road environments. We have gone through all this and make a qualitative assessment if the function could help, if it could make things worse, if it could make it much more positive. And then we have presented results in terms of how common different results are. Sorry, pictograms of lost here. So in this case, we have some very positive results for some accident types and some positive results for some. And I will now leave over to Charlotte and Marcus to tell you on how we have implemented this in microscopic and macroscopic modeling so that assessment is possible.
Thank you, Johan. Before we really move on, let us have a quick round of questions. We are delayed in time, but we really want to make this an interactive meeting. So Wolfgang, you have been looking at the chat, and who has not left a question in the chat, maybe you still want to put one. Wolfgang, what is the result from the chat?
Yes, hello everyone. Welcome also from my side. Happy to see that we have such a high number of participants. There is a clarification question, Johan, which says, or he asked whether all AV classes vehicles refer to level 4 of the SAE levels.
Yes, they do. So that's within the call and in CoExist. And of course, during the transition period, we will have lower levels available as well. So even better if we could have even more different combinations of automated vehicles or partial automated, but yeah.
Okay, maybe a quick other question. So in CoExist, we have mainly analyzed private automated vehicles. Is that right?
Yes, I guess Charlotte can tell you a little bit more about that, but the focus has been on private. It's trucks as well, but it's there's not different driving logics for cars and trucks. It's the same applied.
Okay, thank you. Maybe one quick reminder, you can ask the questions. There's several coming in at the moment. We will try to follow up. As Daniel said, questions which cannot be answered now will be answered in the follow-up documentation. And you can also raise your hand if you would like to have a question directly. And I asked Siegfried now if we have a raised hand here.
Yes, there is a raised hand, but it has gone down. Okay, no raised hand. So we can continue, but please, everybody, use the chat function. You can ask very specific questions, which my colleagues will then ask you individually. I will answer you individually, or alternatively, you can ask a question to the speaker. After each presentation, we will open the floor, and Wolfgang will always look at the chat, and I will look at the raised hands. So whenever a question comes up, please put it in the chat or raise your hand, and then you will not be forgotten if time allows. Otherwise, we will give a written response. But please, let's move on to Charlotte Fléchon. Charlotte Fléchon is the project manager at PDV for transport policy and research. So Charlotte, over to you, please.
Thanks. Hi, everybody. So I think
you should have the mouse.
Yeah, not yet.
Or the
You're in control of the mouse. It has a stronger delay than in the training. I'm sorry.
Okay. Yes. So I will present you the microscopic traffic flow simulation, part of the automation-ready modeling tools we've developed within CoExist. So based on the framework presented by Johan Olsam just in the presentation before this one, we have developed modeling tools to simulate and model automated cars. So, and by modeling tools, I mean the microscopic simulation tool, PDV vSim, but also macroscopic modeling tools through scripts that will be presented by Markus Friedrich but also built-in functionality in PTV Visum. And our goal was to make the tools as flexible as possible to enable the user to explore easily as many different types of scenarios as possible. So how did we do it and which approach did we use? So first of all, we've collected information on automated cars from 3 sources. The first source, I've called it framework. It includes the impact assessment approach Johan has just been presenting us, including the different driving logics, but it also includes information we have collected from the partners, from the literature, or from various discussions. We've also got data from our project partner Siemens from a data collection on a test track in Helmond in the Netherlands. So there were 3 vehicles, 2 automated vehicles following a manual driven vehicle. And the data collection took place on a real traffic environment and in common traffic. It contains an interurban highway and an arterial road. And each loop took approximately 20 to 25 minutes drive, and 30 scenarios have been tested. So that's quite a lot of data that has been studied and analyzed at PTV, and we've tried to extract typical behavior of automated cars. And the third source of information is co-simulations. What we've done here is to simulate an actual automated car in our microscopic software PTV Visum. I mean a car with the same behavior than an automated car in terms of following distances, etc. And we did this in cooperation with BDCOM, which is a French research institute developing its own algorithm on automated cars. And to connect Visum with the driving logic from BDCOM, we needed a software that could translate the vehicle dynamics for Visum. And for this, we've used the software Priscan from our partner Siemens. And to make this a bit clearer, I'll show you a video. If it works, yes. Oh. Almost works.
We never wanted to be one of the conferences where everything works, did we?
No. But it's gonna work. It was working before. But it's a little, there's a little bit of delay when I click. And it's a bit challenging for the internet, probably.
Wolfram, can you maybe click on the play button? Maybe you have more immediate.
And if you can click on 18 seconds or something like this. Yes, it works better with you. Yeah, perfect. Thank you. Yes, so to make this a bit clearer, I wanted to show you this video that we've made for another purpose that was for the ITS Europe in Brainport. So, but what you see here is there are 2 white cars, yes, at the beginning, and these 2 cars, they are controlled by Priscan. And what we've done for our experiment is that in these 2 automated cars, and there will be the control logic from VDCOM inside, and which means the cars, they would behave like a VDCOM car in the model. And the cars you have seen in the background that you don't see anymore, these are generated and controlled by Visum, and that also offers the possibility to perform traffic flow analysis. So we have been using, okay, now we can go to the next slide. Yes. So we have been using the results of the co-simulations to validate the development we have been implementing in Visum. And for example, looking at the results we've gathered, it became very clear that the safety distance the vehicle were keeping from each other was much higher without communication than with communication between the vehicles. And that means we should develop our software so that one can easily simulate mixes from safety distances. And that's we've done with along with many other developments. And here is a list of some new features that we have implemented during the project. So the first one was that, as I said, so we can now set different headway for different vehicle classes, and the parameter values affecting the desired safety distance can be specified per vehicle class of the leading vehicles. And this way, connected vehicles can keep smaller safety distance when following another connected vehicles, but large safety distance when following a human driver or bike, for example. So there is also the possibility to uncheck the attribute use implicit stochastics. This will remove the stochastic variation that are there to represent human drivers' imperfections. And this affects parameters such as safety distances, desired acceleration, desired decelerations, and braking decisions. Then we have the attribute observed vehicles from VSIM 10 that has been split into two attributes, number of interaction objects and number of interaction vehicles. And with objects, I mean stop signs or red signal ahead. And this allows to differentiate between communication and no communication with objects, for example, in a very simple way. It is possible to set higher acceleration in following process in order for the vehicle to stay in touch with the vehicle in front when the speed of the vehicle in front increases significantly and quickly. And this is something we've observed on the results from the test track in Helmond, and we've therefore implemented. So there is also the option to tick on-force absolute braking distance. This means that the vehicle will adapt its safety distance to be able to brake without collision at any time. And this allows to model cautious driving behavior. Then we also have considered vehicles in dynamic potential. So we try again with videos. It looks better. Start the second one. Okay, so a vehicle blocking a conflict area can now be considered in the dynamic potential for conflicting pedestrians. And if this option has been activated on a pedestrian link, pedestrian will not stop at a blocked conflict area, but will try to walk around it through the gaps between queue vehicles. And you can see on the video that when the dynamic potential is off, which is a video on the top, the pedestrians are not very smart. And they stay on the side and don't find a way to cross. I don't know if it's working for you, but it's a bit weird on my screen. I hope it's better for you. And when it's on, so it's what you can see at the bottom of the slide, they find the gaps between the cars and cross the street. And this allows to better simulate shared space. So I hope you believe me if you cannot see it. So another feature is the zero passenger feature. It's possible to set the number of people in the car to 0, which is quite useful for empty automated cars. Then we have a driver model and driving simulator that have been improved. These are APIs improvement that allow the user to connect VSIM to other softwares or use external driving behavior. And this has been used, for example, in the co-simulation I've shown you before to connect VSIM and pre-scan. Then we have lane-specific driving behavior. I think the title says it all, so one can assign different driving behavior depending on the lane. And finally, platooning. And the last video. So that's a new feature that has been released in vSim 2020. It's a built-in platooning feature. So cars can connect to each other to form platoons, as shown by cars standing into blue in this example. And by platooning, I mean connected vehicles traveling very closely and safely together, and also at high speeds. So now it's possible to study the effect of platooning on traffic flow without the need of scripts. So we have also made this table available. These are recommended values for the parameters of car following models. So that's Widerman 99 and Widerman 74. And these for the different driving logics that have been developed within CoExist. And it's important to note that these are only recommended values. So it means we have estimated them with the best of our knowledge, but these values could change with new learnings on the behavior of automated cars. But we think it's at least a very good starting point for your simulations. So I've presented briefly some new features that have been implemented in vSim. And tomorrow, my colleague Peter Zukenik will do a training on vSim. So if you want to know more, then you can attend this training. Exactly. And so the next step of the project has been to use the results from micro simulation models as the base for creating assumptions for the supply side of the macroscopic travel demand model. And so for this, we've given University of Stuttgart results from microscopic simulations in form of maximal throughputs and fundamental diagrams of the traffic flow for selected networks and for different driving logics. And based on this, the University of Stuttgart has been developing the CoExist macroscopic modeling tool, and Markus Friedrich is going to present this to you in a few minutes. And at PTV, we have also been improving our software PTV Visum with some building functionalities that have been released this year or last year. And this is not going to be presented today. That's why I just want you to be aware of it, and would then advise you to look online at the webinar and on the CoExist website. And as we have already said before, there are a lot of materials available on the website for modeling tools and also for the other work at CoExist. So I would strongly advise you to have a look at them. And with this, I'm done with my presentation.
Many thanks, Charlotte. So, Wolfgang, what are the questions in the chat? If you have not used the chat function, please put your questions there. Any question?
No, we have received some questions. We have received some questions, yeah. But is there also Paul from Charlotte, or?
Oh yes,
not?
Yes.
Sorry. Yeah. We should maybe do first the poll then.
Yes. I'm sorry.
Okay, so I launched the next poll now. The question is, how important do you think will be the role of modeling tools to prepare the transition phase? And you'll have 20 seconds to choose your answer, please. Five seconds left. 3, 2, 1. I'll close this now and share the results. Seems that most participants do think that it's really important. The role of modeling tools, crucial or important. Only 2% said that it's not important at all. So I think that's really saying something.
Okay.
Okay, thank you very much, Marie. So I would like to maybe have two questions. As said, all the other questions will be forwarded to our colleagues and answered in the follow-up documentation. There's a question from our US Advisory Board member, Stephen Schledover. Has the model of pedestrian behavior in shared space, which you showed, Charlotte, been calibrated or validated with real-world data?
I think that's a question maybe for this afternoon, because not this, yeah, we are already in the afternoon, sorry. So the share space, this has been simulated by VTI, so maybe they can say more about this. But for the, if you are talking only on the functionality in vSim, we're always using calibration, so that's for sure. But the details, we have to, I can try to answer you directly then later.
Okay, and we come back to Johan maybe then later when he represents the use case. There's one other question. As per my understanding, only car following variables were collected during real life data. Thus, the lateral control and lane change variables in PT-Vism of the driving logics are validated and can be used as recommended variables. Quite a long question.
Yeah, we mostly add the data on the car following. We wanted also to have data on the lateral behavior, but unfortunately, during the, so in the different scenarios that has been run, there were not much about this, which means so a lot of it is only what we guess would be good, so would be realistic. But yeah, we mostly had the data on the following model.
Okay, thank you for this. I see a raised hand, Siegfried, so I will give it.
I will give the word to Erfan Arya. Are you ready to speak? The microphone is open to you. Would you like to ask your question? Okay. Sorry, there seems to be a technical problem. The microphone is open. If you want to speak, you can speak and put your question. Okay. I'm sorry.
So, Siegfried, it's me, George Saros.
George, please.
In the meantime, may I ask one question?
Of course.
Thanks. Regarding the new features, I mean, it was about the last presentation about the microsimulation tools. Regarding the new features and the modules and submodules, how open these modules are in order maybe to be used from another microscopic tool?
So when they are building functionalities, then they are not open. But for example, the recommended values for car following models, they can be used with any software offering car following models. Yes. So that's for the microscopic. And for the macroscopic, what Marcus will present, these are scripts that are open.
Okay. Thank you very much. Because we are still a little bit delayed, I would like to move on to our next presenter, Professor Markus Friedrich from the University of Stuttgart. So, Markus, please.
So I'm waiting for the mouse so I can move the slides.
Good to go.
Okay, it's not yet happening, but I'll try again. Okay, see if that is fine now. So welcome to my presentation on macroscopic travel demand modeling. Now this mouse doesn't work. Okay. Automated vehicles may change the way we traveled. automated vehicles are obviously better than the cars we have today. So if cars become better, we are likely to travel more by car. Automated vehicles make car sharing easier, but also easy car sharing may jeopardize traditional public transport. Therefore, we may end up with more car traffic on roads. But maybe we use automated cars in a different way. We do not only share vehicles, we also share trips. And a good public transport supply with integrated ride sharing could reduce car traffic. A travel demand model is a tool which enables us to examine potential developments in both directions. Now the slide should move on, which it doesn't. Okay. In CoExist, we developed tools for macroscopic travel demand modeling. Many cities run macroscopic travel demand models and may want to examine impacts of automated vehicles. Macroscopic travel demand models assume that people live in zones and the demand is represented not as full trips, but as probabilities. This is a challenge when modeling on-demand services. Imagine a demand of 0.4 trips requesting a free space in a sharing vehicle. A travel demand model replicates typical decisions of persons in specific steps. Trip generation determines the number of trips. Destination choice determines the location of an activity, followed by mode choice, departure time choice, and route choice. With cars of automation level 3, we may see changes in capacity. This can influence the performance, route choice, and travel time. Furthermore, car drivers can use some of their in-vehicle time for non-driving tasks. This can influence their perception of travel time. And with driverless cars, we need to look at new modes and additional decisions. Will people decide to give up their private car? How are persons trips pooled to vehicle trips? And how are shared vehicles scheduled? This presentation addresses 3 aspects of automated vehicles: modeling the impacts on supply side using volume delay functions, modeling the impacts on demand with level 3 and level 4 cars, where we still have cars which require a car driver, and modeling the impacts of demand assuming driverless cars are available, which enable new modes of transport. Assignment models use volume delay functions. Today, we distinguish light-duty vehicles and heavy-duty vehicles. To consider their characteristics in the assignment, it's common to use the concept of passenger car units. A vehicle which requires more road capacity than a passenger car is assigned a passenger car unit value larger than 1. For example, typical value for trucks is 2 passenger car units. In an assignment model with automated vehicles, we can apply the same concept. An automated vehicle which is more capacity efficient may have a passenger car unit value of 0.8, for example. To determine suitable passenger car unit values, we performed a large number of microscopic traffic flow simulations with vSim. Actually, PTV did that for us. We distinguished 3 types of roadways: motorways, arterial roads, and urban streets. And in addition to manual driving, we distinguished three types of driving logics which were presented before: cautious, normal, and all-knowing. So we combined this to three AV classes: basic, intermediate, and advanced. Then we looked at the capacity impacts of each class using specific sets of passenger car units. For example, the AV class basic, we assumed manual driving for urban streets, which corresponds to no changes in the passenger car units. Automated vehicles have impacts not only on capacity, but also on demand. Using an AV of level 3 or level 4, drivers can use some of the in-vehicle time for non-driving tasks. For example, they may read or send messages. This can change the perception of travel time and make the mode car more attractive. Now, how can we model that? Assume a city has a calibrated travel demand model. This model will include a scheme matrix for the mode car. This matrix describes the supply quality for every origin-destination pair. And this supply quality influences destination choice and mode choice. We now add a new transport system, automated vehicle, and we assume a certain share of automated vehicles. We now compute additional schemes for AV. This is the matrix here in blue. This scheme matrix describes the perceived travel time of automated vehicles. To use our existing travel demand model without any changes, we now compute the weighted average of the perceived travel time for conventional and automated vehicles. And then we run the demand model again with this weighted scheme matrix, and we get new shares, new modal shares for each mode. Here are some results from a model application in the Stuttgart region. In the scenario, we assume the availability of advanced AV, which can operate on motorways and on main roads. Assuming a reduction of travel time perception of 30%, we get the following results. The total distance traveled increases by 7% if we assume that motorways are AV ready. And the total distance traveled increases by 15% if we assume that motorways and main roads are AV ready. Here you see the increase just for the mode car. So this is an increase around 11%, 23% in the case of the Stuttgart region. This means that public transport is losing passengers. Fleets of driverless vehicles can enable on-demand services in the form of car sharing or ride pooling. For ride pooling, we need to pool person trips to vehicle trips. This requires a matching of trips with similar temporal and spatial pattern, so they must overlap to a certain extent, and we need to consider the capacity of the vehicle. We developed an algorithm which can pool trips for macroscopic models where the demand is non-integer. We achieve this, we still look at the overlapping, but we achieve that by looking at the volume, the demand of the first OD pair. We take this demand and multiply that with the capacity of the vehicle. And then we try to fill up this vehicle with trips from additional OD pairs. This matching algorithm splits the demand into time intervals. For example, We split the day in 19 time intervals of 15 minutes each. Then we assign every link to a specific zone and compute shortest routes between the zones. And this is the basis for the matching. But the trick is that for the matching of two passenger routes, we do not need they do not need to overlap on the level of links. It's sufficient if they overlap on the level of zones. So we just look at the reduced sequence of numbers, because those automated vehicles, they can perform certain detours to pick up the traveler in zones. And finally, on-demand vehicles of a car sharing system or a ride pooling system will be reallocated, similar to public transport today, to collect the next customer. Yeah, this is the case today. We have two vehicles and we have two trips. Now in the future, those vehicles, driverless, can be reallocated, and that leads to a trade-off. We reduce the number of vehicles, but we end up with more vehicle trips because we have this empty trip in our network. To determine the number of vehicles and the empty vehicle trips, we developed a scheduling algorithm to consider the characteristics of macroscopic models, so non-integer demand. We formulated the problem as a flow problem. And with this algorithm, it's possible to compute a trip table which contains all empty trips, which then can be assigned to the network. Everything I showed you can be integrated into the software Visum to support AV-ready demand modeling. That's my slides. Thank you for listening.
So before we go to the questions that have been coming in, I would like to show you another little poll. So the question is, how will AVs affect travel demand by 2040? Please note that you can select several of those options, and the penultimate option means integrating ride sharing into public transport will strengthen public transport. So 20 seconds on the clock. Already have 30% of participation, which is quite great.
While we're waiting for the results coming in, let me say what a great audience you are. We have 110 attendees, between 105 and 110 all the time throughout the webinar. So that's really great. And participation levels are also very good in the voting. So thank you to you all. Back to Marie.
Now you had a little more time, but I'll stop now in 3, 2, 1. And also I'll share the results right away. So apparently, according to the audience, several of the factors are really important. The most important one will be that AVs can be used for sharing and will reduce car ownership. And another fact that's been considered important is integrating ride sharing into public transport will actually strengthen public transport. Max, do you want to say something to the results?
Interesting results, because it basically says we don't know.
Yeah, well.
So you have the entire variety which may happen, more cars or strengthen public transport. So this is why I think modeling is great, because we don't know, but we can discuss various options. And yeah, so we can maybe be prepared what may happen in the future.
Okay, thank you, Marcus.
Okay. Yeah, thank you, Marcus. Questions coming in, maybe one for clarification. It's related to a term you used at the introduction of your speech. What do you mean with better cars? in terms of automated cars?
Well, every car you buy is better than the car you had before. So even the cars we have now, which may be automation level 2, they make the car more attractive. And I think even if we are not jumping to driverless cars in one step by step, cars will become more comfortable. Part of that will be driving logics or driving assistance systems. And the mere fact that cars become better, it's going to make them more attractive. And the very moment you have those assistance systems, yeah, you can use some of the time in congestion or in front of a traffic light for different things. People are already starting that today. And that, yeah, that will influence road choice, one may believe.
Okay, thank you. Here's one further question from, without saying names, from a further student of yours, Marcus. How was the assumption of 30% reduction in perceived time selected? So how did you come to this assumption?
Well, we varied it. So later on this afternoon, you will see that we have 0%, 15%, and 30%. It's an assumption, but you can justify it by looking at the way people traveling by public transport, especially on trains, how they perceive travel time. And usually people travel longer distances, even in commuting, by rail, not by bus. If you can sit relaxed in a vehicle, not being responsible for driving, this value between 0.15 and 0.30 reduction is a reasonable assumption.
We have one, I don't see a raised hand, and we have one presentation still to come, so I hand over to Siegfried.
Well, not much handing over really, except jumping across the Atlantic Ocean. Rachel, are you there? Rachel, maybe you remember to unmute yourself. Our colleague Rachel James from the Federal Highways in the United States. Federal Highways is the highway agency of the US Department of Transport. Welcome, Rachel. Good morning to you. How are you doing?
Good morning. Can you hear me now?
Yes, we can hear you very well. You want to get started
Very
right
good.
away?
Yes, please.
Maybe just word of context. Rachel and colleagues were our twins. So we had a partner project in the US and we exchanged regularly. We are quite similar in many respects and dissimilar in others, but please hear yourself. Rachel, thank you for joining so early.
Thank you so much. All right.
You should have control of the mouse and keyboard. So if you advance, yes, looks good.
Okay, it's not changing on my end. I'm going to turn off my webcam and see if that helps. Oh, there we go. So good morning, everyone. My name is Rachel James, and I'm a research civil engineer for the Federal Highway Administration. I am also the FHWA lead for the twinning agreement with the CoExist project. And my presentation today is entitled Toward the Development of Analysis, Modeling, and Simulation Tools for Connected and Automated Vehicles. Siegfried or Daniel, would one of you mind just advancing the slides for me? There's a significant delay.
Yes, there is a delay, but
Perfect.
also others have it. I think Wolfram, who's closest to the presentation, Wolfram, you can maybe advance. Okay?
Okay, I will take over, yes.
Thank you. All right, so really quickly, there were two FHWA projects that were twinned with CoExist. They are the Connected and Automated Vehicle Analysis, Modeling, and Simulation Tools Framework, or CAV-AMS, and the Developing AMS Tools for CAV Applications, which had two pieces, case studies and tools development. And the goals of these projects were to investigate the effectiveness of level 1 automation technology for mitigating or solving existing transportation problems. So that's a key difference with our projects and CoExist, is that CoExist, as you've heard today, focused on higher levels of automation. We were really focused on the near-term impact. So we focused solely on level 1, and we also incorporated connectivity into all of our projects. Next slide. So the development of a CAV AMS framework was really the cornerstone piece of our research program. And there were 3 objectives. The first was to build a comprehensive methodological framework for developing analysis, modeling, and simulation tools incorporating the impacts of CAVs. And you see a high-level picture of that on the right-hand side of your screen. The second objective was to conduct an analysis identifying gaps in existing CAV AMS capabilities. And finally, we applied the developed framework to conduct a small-scale case study to illustrate how to use this framework for future development activities. And so the framework really has 3 pieces. It has the demand effects, which you see in red, and that's looking at how CAVs are going to change the way that we behave. Is it going to increase demand or decrease demand? We also have captured supply changes, and that's looking at how the supply of vehicles will change over time, and gets into questions of, will these fleets be privately owned and operated, or will they be shared similar to how we treat transportation network companies? And then the third piece is in blue, and it's the operational performance. And that's getting at how CAVs and human-driven vehicles are going to behave inherently differently, and those behavioral differences need to be captured in our models. And then the yellow piece in the bottom right-hand corner, that's network integration. And so it's recognizing that the demand effects and the supply changes and the operational performance, they're not independent of one another. They're all interconnected. And so it's going to be really important to make sure that these different areas feed and inform the other types of models. Next slide. So the second project is developing analysis, modeling, and simulation tools for connected in-vehicle applications. And the first piece of that is case studies. And so these were benefits assessments using existing tools and capabilities. We had 4 case studies. 2 of them were located on signalized arterial corridors, and those were in Ann Arbor, Michigan, and Conroe, Texas. The second 2 were located on high-speed freeways, and they were State Route 99 located in Sacramento, California, and I-66 in Northern Virginia. And a key piece of these case studies is that local agencies were involved to ensure that the simulations that we developed represented realistic and near-term deployments. So everything in our case studies, they're all things that some of our state and local agencies are seeing as feasible options in the near future. Next slide. So we'll begin, or for the sake of time, we'll talk about the 2 freeway case studies, which were I-66 and SR-99. So the motivation of the SR-99 case study was to study the impact of cooperative adaptive cruise control, or CACC, on complex corridors. And so we know from the literature that initial studies suggest potentially significant increases in capacity on IDLS corridors. However, there's a significant need to better understand the impacts of CACC on real-world freeway networks. And the reasons for that are twofold. We recognize that congestion is complex and that the patterns that we see result from the interplay of multiple bottlenecks. And so there's a real danger that the throughput improvement at one bottleneck may aggravate congestion at downstream bottlenecks. And so we can't really look at this in isolation. We need to be looking at how it's going to be happening in the real world. And so to that end, State Route 99, which is an urban corridor serving commuter traffic in California, was selected for detailed analysis. Next slide. The objectives of the SR-99 case study were threefold. But before getting to that, the framework, so going back to the framework piece that I was talking about initially, this work predominantly focuses on the operational performance piece, and it contributes to the literature by developing an improved CACC simulation algorithm and quantifying the impacts of CACC on a complex network. Next slide. There we go. Now we get into the objectives. So the objectives of this case study were threefold. One, to evaluate the impact of the CACC application on the network. Two, to look at the impact of a CAV managed lane operational scenario. And three, to look at the impact of a vehicle awareness device, or VAD, which provides connectivity for manually driven vehicles. And so the idea behind the VAD is that you're giving connectivity to a manually driven vehicle. So the manually driven vehicle cannot behave as a non-leader in a CACC string or a group of consecutive CACC vehicles. However, it can serve as a leader. Next slide. So we'll begin at looking some of the results. And so the effect on CACC market penetration rate, you can see on the right side of the screen that speed increases as a function of the market penetration rate. And that's really because of the smoother traffic that we see attributable to the CACC application. Fuel economy is a different story. We see initial benefits to fuel economy because of the congestion relief. However, at higher travel speeds, you see that decrease in fuel economy because it's no longer operating in that optimal range of the vehicles. Next slide. So next we looked at string length. So again, a string of CACC vehicles are a group of CACC vehicles that are operating more closely. And what we see is that as market penetration rate increases, the string probability increases. However, at 100% market penetration rate, we see a lower string probability than what we would probably expect. And so what that suggests is that a string formation algorithm is likely needed to increase the probability that CACC capable vehicles actually drive in CACC strings. Next slide. Next, we look at the effects of traffic demand increase. And so this was really getting at how much capacity increase can we truly get with higher market penetration rates. And so what we did was we looked at what the average travel speed was at 100% demand with 0% CACC. And you see that in the upper left-hand corner, you get about 33.4 miles per hour. And so as we increased the CACC market penetration rate and the overall demand on the corridor, we looked to find those boxes where you see about 33 miles per hour. And so we were identifying the corridor capacity increase as the point where you're maintaining a constant average speed. And so you see almost a linear relationship at a 100% market penetration rate of CACC, you're supporting about a 30% increase in demand. And that's significantly lower than what we observed when we were looking at an isolated bottleneck case, which you'll see on the next slide. So what you see here is that on that isolated bottleneck case, there's about a 92% increase in capacity on the freeway. Whereas when we look at the freeway corridor case, you're only seeing about a 30% increase. And the reason is what we suspected, and that's that by mitigating some of the issues upstream, you're worsening some of the bottlenecks downstream because they're seeing more demand than what they can handle. And so what that suggests is that we might need other I2V or infrastructure to vehicle applications like speed harmonization to maximize the freeway corridor performance. Next slide. Finally, we're going to look at the impact of the vehicle awareness device and the managed lane strategy. And what you see is that the vehicle awareness device indeed helps improve the probability of string formation, particularly under low to medium market penetration rates. And when we look at the effect of the managed lane, it actually makes performance worse because it's causing induced lane changes as the CAVs try to get over into the managed lane. And so one of the hypotheses that came out of this research is that dedicated on-ramps might help the managed lane strategy implementation. Next slide. Which transitions nicely into our I-66 case study results. And so before we get into the results, the objectives of the I-66 case study were to evaluate the effectiveness of 3 CAV applications: CACC, speed harmonization, and cooperative merge. And this case study also evaluated the potential benefits of changes to the physical infrastructure, including dedicated ramps and a managed lane. Next slide. There were 3 different managed lane strategies, or before we get into that, we'll go back to the framework. Again, the primary contribution here is in, oh, nope, we're going to talk about the managed lane strategy first. So there were 3 different scenarios that we looked at. Scenario 3 is where you, that's real world. So there's no dedicated on-ramp, and CAVs and CVs are not allowed to occupy the managed lane because they're not high occupancy. In scenario 2, we relax that assumption and we allow high occupancy vehicles and CVs and CAVs to access the managed lane. And then scenario 1 is kind of the idealistic scenario where we allow the CVs and CAVs to access the managed lane. We also build a dedicated on-ramp. Next slide. Now we get into the framework. And so again, the contributions of this work was in the blue box, the operational performance, looking at the heterogeneous traffic interactions. And so this work contributes to the literature by developing a speed harmonization and cooperative merge algorithm for microsimulation, quantifying the impacts of these applications, and exploring the impact of different infrastructure configurations. Next slide. Getting into some of the I-66 case study results, what we observed is that predominantly the CACC strings are what are generating most of the traffic flow benefits. However, like what was hypothesized in the SR99 case study, when you bundle CACC with speed harmonization and cooperative merge, you get further traffic flow benefits, particularly when the market penetration rate of the technology is low to medium. Next slide. Finally, we look at the impacts of the managed lane scenarios on the quarter performance. And as kind of expected, the managed lane 1 scenario, where you have the dedicated on-ramp and allow the CAV and CV vehicles to access the managed lane, generates the most benefits. Whereas the status quo, where only HOVs are allowed to access the managed lane, sees the least benefit. However, managed lane scenario 2 outperforms scenario 3. And so what that tells us is that the dedicated ramps help improve traffic performance. However, if there's not the funding allocated to build a dedicated ramp, you still see benefits just by allowing the CAVs and CVs to access the managed lane. Next slide. So like I mentioned, there are 2 pieces to this developing AMS tools for CAV applications: the case studies and the tools development. With tools development, the focus is on developing new tools to enable more robust impact assessments. And there were 4 tools that we developed. All are open source. The algorithm description documents and the algorithms themselves will be posted online at the completion of the project. So you will be able to download these and use them in your tools as you see fit. The 4 tools that we developed were a new automated vehicle lane changing algorithm, an improved CACC algorithm, and a new human driver connected vehicle car following algorithm, an improved speed harmonization algorithm, and a new cooperative merge algorithm. Next slide. Okay, so in conclusion, there were two projects that were funded by the Federal Highway Administration that were twinned with the CoExist project: the CAV AMS Framework Project and developing AMS tools for CAV applications. The primary contribution of the framework project was that it developed a comprehensive methodological framework for developing AMS tools incorporating the impacts of CAVs. On the tools project, the contributions were twofold. One, we conducted 4 case studies on complex freeways and arterials in the US to evaluate the benefits of this technology. And 2, we developed 4 new models of CAV driving behavior for incorporation in microsimulation softwares. Like I mentioned, they're open source, they will be posted online, and so you'll be able to download those and use them in your research. Next slide. And with that, I conclude my presentation. If you're interested in the framework project, that is reference number 1. The references for the 2 case studies projects are 2 and 3 on the reference list. And then the tools development, we're in the process of reviewing the final report now. And so that's probably about 6 months to a year away from publication, but it will eventually be posted online for you to use. With that, I thank you for your time, and I'll take any questions.
Thank you very much, Rachel. We are a little bit behind time now, accumulated some delays. Wolfgang, what are the questions in the chat? And I suggest to drop the poll just to have a few questions.
Yeah, I think we should have at least one question, even time is already up. But yeah, thank you very much, Rachel, also from my side for getting up so early today. We have maybe also for future twinning cooperation programs or agreements, maybe the question, what is next in the perspective of CAV's research from the US side? What are your plans?
Yeah, so at this point, one of the gaps that was identified in the framework project that was twinned with CoExist is that one of the pieces that are really hindering the development in this area is the availability of data on which to build models. And so in the US, we have a couple of projects that are coming online that are designed to fill that need. We have a project that kicked off last year that will be using the Karma platform at Federal Highway to collect driving behavior about the Karma vehicle itself, but it will also be collecting data about the vehicles surrounding the Karma vehicle. And so particularly at lower market penetration rates, as this technology is coming online, the human's reaction to the automated technology is going to have a huge impact on the traffic flow performance. And so we're really focused on collecting that data that allows us to start answering those types of questions.
Okay, thank you very much, Rachel. I think we're at the end of the first part of the session then, Siegfried. And also, if there are further questions to Rachel, of course, we will forward it and provide you with the answers in the follow-up documentation.
There is one raised hand, and I need to apologize. Could you please put your question in the chat, and you will get a response. As every question that has not been answered, we will put up an FAQ, and we will send out all the material that originates from this project, including a link where you can listen to the recording and other material from the project. So we're taking a break now. We are 10 minutes delayed, more or less. I suggest we take 10 minutes break and resume the meeting at 15:50. So enjoy your coffee and see you in 10 minutes, please. I suggest that you all stay on and just leave everything as it is if possible. See you and enjoy the break. So welcome back. I hope you have had the chance to have at least a coffee, say. Before we continue with the program, for those who have arrived for this part particularly, I would like to invite Daniel to give us a very quick reminder of the interactive features of the webinar program. Daniel, are you here?
Yes, hi Siegfried. Thank you. Wolfram, do I have the control of the mouse? Or maybe can you go through the slides for me? That's okay. Actually, these are hidden, I believe, these slides. So I can just very quickly mention what we can do with the functionality. Please be aware that you can change your audio connection in the audio panel. We also have the option of raising your hand because you're all muted automatically, but you can raise your hand to basically alert us of that you want to say something, you want to pose a question. So we'll be on the lookout for that. There's also a question box where you can input your questions for the speakers, and we will read them as we did in the first section. And there's also handouts which you can download, and we'll have some polls coming up. So thank you. There's an instructive in the handouts with more detailed explanation of this for your guidance, and emergency hotline numbers. You can contact us.
Okay, super. Thank you, Daniel. So we move to the second part. The second part, as you can see from the program, is about presenting the findings from the impact assessments of our use cases. As it was mentioned, we've had 4 cities, and each of those 4 cities had 8 use cases. And the first one is Helmond. Frank, are you ready? Frank van den Bosch, he works for the city of Helmond, and he's going to present the results from his city. But before that, we are starting with a poll. Marie, can you present the poll?
Hi guys, yes, welcome back from my side as well, obviously. I'm going to launch the first poll of the second part, and I hope many of you are already back to respond to it. So our question is, what do you think are the primary reasons for developing CAD? And as you can see, you can also, again, choose several answers. I'll put 20 seconds on the clock now, so take your time. If you select the least option, you can also send your other suggestion in the question box and we can read it out. Okay, so you have 5 seconds left. 3, 2, 1. Now close it and share the results right away. So one of the most important reasons, according to you guys, is improving safety and increasing mobility options. With over 50%, the other reasons, improving productivity and reducing congestion, have also been considered relevant to at least 1/4 of the audience. And then we also got a few answers via the questionnaire. So other reasons could, for example, be to reduce car ownership and to reduce the operation costs of public transport in low density areas, which I find really interesting as well as potential reasons. Thank you guys, and back to the presentation.
The control is yours, Frank. And you should unmute yourself, please.
Okay, unmuted. Hope you can hear me all. Good morning and good afternoon to you all. I will present 2 use cases from the city of Helmond. Try to switch to the next slide, but it has some delay, I heard before, so. Okay, first of all, it's the first use case presenting, but in the project it was use case 3, so that's where you find here use case 3. It's about a signalized intersection with cyclists and pedestrians. It's on the main road in the city of Helmond, and there are large volumes of car traffic, which are not seeing in the picture from above. And there's also a crossing of cyclists and pedestrians, mainly in the north-south direction. And the research question we as a city had in this use case was, is the performance of the intersections getting better? Is it depending on the penetration rate of the CAVs? Is it depending on the kind of CAVs? And is automation enough to produce benefits, or is there also need to be connectivity? The model includes cars, trucks, cyclists, and pedestrians. And there's also been a connection with the inflow simulator. Inflow is the adaptive traffic light controller we are using in Helmond. And there was a real connection with the traffic light, with this traffic light controller. And here you see small footage of the model. The scenario specification, we did, as thought before, there are a lot of different mixes in this observed. In the introductory phase, we used 25% of AV penetration, in the established phase 50, and in prevalent stage 75. And there's also a different mix of AV classes in the basic, intermediate, or advanced AV share. The first results of the impact of the traffic performance, you see that the traffic performance in travel time for cars and trucks will become worse. That is mainly, I think, caused by the due of that normal cars in this in the normal situation are speeding, and AVs are not speeding, so the travel time will become a bit longer. And also due to the adaptive traffic lights, there's some small gain for bikes and pedestrians in the prevalent stage. In the delay, you see slightly improvement during the stages. In the first stage, there's more delay, also caused maybe by the cautious vehicles, but becoming more and more advanced, the AVs in the prevalent stage, you see that the delay will be lower. We want to implement a measure also in this use case. The measure we wanted to implement was priority for AVs on the intersections. In the Netherlands, we are implementing so-called intelligent traffic lights, which can communicate between cars, and that there's communication between cars and traffic lights. The measure we want to implement was priority for these traffic lights, but due to technical problems between the inflow simulator and VisSim, it was not possible to test that. But in another project we did in Helmond, and that was called Maven, another Horizon 2020 project, this was also tested, also by simulation, but also in real life. And we also saw that negotiated driving with the adaptive traffic control, there was a large relay on a large reduction of delay time. So at the end, we think that when cars become advanced and also connected, there will be space to reallocate green time in advance of pedestrians and cyclists. So the conclusions of this use case: in the early stages, travel performance will get worse. In the prevalent stage, performance will improve, which is mainly the result of the advanced AVs with connectivity, because the advanced AVs, as was told before, had some a number of cars which could interact, or objects which could interact with, and that was so it could look in advance with other cars, but also traffic lights. And when AVs become more sophisticated in the prevalent stage with connectivity, there would be space to reallocate green time in favor of pedestrians or cyclists. The other use case 4, that's the transition from an interurban highway to an arterial. It's also on the main road between Eindhoven and Helmond, which changes from interurban motorway to an urban road. And there are different speed limits and different traffic conditions. And here also the main questions were: can CAV improve traffic conditions? Will the speed become more homogeneous to the presence of CAVs, or will it also lead to a more efficient flow? And does it depend on the penetration rate or the kind of CAVs? As you here see, it's a long stretch with different speed limits, also with 4 signalized intersections. And daily there are 35,000 cars on the main road. It was also a microscopic model including cars, trucks, cyclists and pedestrians. On 2 intersections are cyclists and pedestrians. There was also here the connection with the inflow simulator, so the real implementation of the adaptive traffic light controller. And as a measure in this use case, we implemented platooning. Here the same scenario design, different penetration rates, different AV class mixes, and also different. We also had different demands and also different measures. The results of the traffic performance. First of all, as the same as in the other use case, you see the travel time getting longer in the use cases, but there is some gain in the prevalent stage of the delay for cars and trucks. Here you also see the travel time will get longer, mainly by the AVs, which are in the gray bars, and the delay will become less. So we had 2 measures. Measure 1 was platooning on both of the 2 lanes. As you can see here, the blue cars are in a platoon, and they're also on the right and on the left lane available. And the other measure was only platooning on the right lane. As you can see in this video on the right side, only cars are in a platoon on the right lane. And the results of the platooning. Here you see also a bit of more travel time, but a larger gain in the average delay for cars and also for trucks. That was for platooning on both lanes. For platooning on one lane, it was almost the same result, but a little bit less than in the one before. What you also could see was that platooning on the highway and arterial reduced speed. When speed was in the base 100%, then in the prevalent states it was reduced by 7%. And you also see that travel time, first of all, will become a bit longer, and later on it will be less and less, almost the same as in the normative. What you also could see was that there was a gain in space-time utilization in the prevalent stage, and due to the space-time utilization and also the delay and the adaptive traffic light, you could see that there is a large gain also for the bikes and pedestrians in the prevalent stage in their travel time and also in their delay. The conclusions of this use case: travel time increases for CAVs in comparison to conventional cars, also given to the full speed compliance. In the introductory phase, also increased delay for vehicles due to the cautious driving behavior, and during the stages and AVs become more sophisticated, there's a decrease of delay for all traffic. Enabling platooning in both measures result consequently in shorter delays, and also similar increases in travel time. And because of the delay and the better space efficiency, here also there would be some time at the intersections to reallocate green time, of course depending on the city policy.
Thank you very much, Frank.
You're welcome.
We now have a poll coming up, and while Marie, please, over to you.
Thank you, Frank. I'll launch the poll right now. So after Frank's presentation, we would like to know, when do you, the audience, expect a noticeable effect from AVs on the road, and for example in your city? Please select one. We already have quite a good participation, almost 30%, and I'll give you another 10 seconds. Really nice, thank you. I'll end the survey in 3, 2, 1. And I will also share the results right away. Seems like a majority thinks that between 2035 and 2050 we will noticeably see AVs on the roads. Some people are less optimistic and looking at 2050. But yeah, seems like the majority is positive that we will see AVs rather sooner than later. Thank you.
Okay. Thank you, Marie. Wolfgang, what are the questions in the chat?
Yes, hello everyone. There is an interesting question regarding the assessment of the results in terms of traffic flow, Frank. So what does the city of Helmond intend to do to reduce the car use? Isn't reducing car use more effective than expecting prevalent AVs?
Yeah, we are gaining on both, I think. We also we think AVs will come, so that's why it's necessary to participate in this project to see what will happen to our city. But we are not only promoting AVs, or and that's also we want to. That's why we want to maybe reallocate green time for bikes and pedestrians, because we think it's also important. So we have also other measures to reduce maybe the car use. But we think, yeah, just like a mobile phone, also AVs will come to our city.
Okay, thank you. There's one more technical question. For the use cases, was there any lane change behavior incorporated? The lane change was the normal lane change, as in
what was in Visim available.
Visim.
Yeah.
Okay, thank you.
Okay,
I don't see any raised hands. Sorry.
Yeah. So, any questions? Any more questions? Not now. So thank you very much, Frank.
You're welcome.
We move on. And our next speaker is Iman Pereira from Gothenburg. So welcome, Iman.
Yeah, thank you, Siegfried. Well, we're sitting in Linköping actually, but the use case is Gothenburg, yes. So, but it's good. You can hear me.
Indeed.
Yes. Okay. Yes. So as Siegfried mentioned, my name is Iman Pereira, and I'm going to talk a little bit about the use case 1 in the Gothenburg for Gothenburg City. So use case 1 is this shared space located in the city center of Gothenburg, and we know it as Kungstorget. And Kungstorget is characterized by very large volumes of pedestrian traffic and small volumes of car traffic. We have approximately 3,000 pedestrians per hour and 50 vehicles per hour during peak. So for the city of Gothenburg, CoExist is not only a huge EU project, it's also this opportunity to investigate the effects of the introduction of an automated last mile service. We want to know if it's feasible, if there's any negative effects on pedestrians and conventional traffic, and if so, we also want to know if the area can be redesigned to improve the traffic performance of the car traffic without making it any worse for pedestrians. So in order to do this investigation, we created a model, and this is a microscopic Visim model, which includes pedestrian and cars. And sorry for the delays. Yeah, well, the modeling technique we used is quite unorthodox, and it's not the one that was shown before here. We've implemented some scripts that essentially what they're doing, they're tricking pedestrians to react to vehicles as if they were two very large pedestrians. And the script is also defining a conflict area in front of the vehicle, representing a sensor. So if the vehicle senses a pedestrian, it will simply stop. And the result is what you see here to the right, even though it's a bit, fidgy. So no, we've not directly used the driving logics implemented in Visim. We've used them for interaction between vehicles, but not for interaction between pedestrians and vehicles. So having a model, we can set up our experimental design. And the experimental design is developed in an attempt to capture all these uncertain factors that Johan talked about earlier. And we've selected 3 penetration rates, 1 for each stage of coexistence. And here you can see in the figure that for the introductory stage, we selected a 50% penetration rate, where all of these vehicles are assumed to be basic minibuses. In the established phase, we start including privately owned AVs, where we have intermediate cars, and then 2/3 are intermediate minibuses. And in the prevalent stage, we have a 90% penetration rate with approximately a 50-50 split between advanced car and advanced minibuses. We've also run our simulations over 3 demand configurations, 3 pedestrian populations, and we've included 1 measures, and this results in 42 experiments, which take approximately 40 days to run. The runs then give us a range of results in each stage, which are illustrated in this figure. So before I start talking about this figure, I just want to clarify a couple of things. Car CV here is conventional cars, so conventional traffic, and car is conventional cars and automated cars, just so you're on board with that. Also, the minibuses here, in each stage, we've assumed that the whole fleet of minibuses is automated, so the results here are basically shown for automated BT buses. So the range that I talked about is depicted in the error bars, and the bar itself is the median of the results, and you can see by the color which stage we are in. So a couple of things that I want to touch is, first, yes, the pedestrians are barely affected at all by the introduction of AEVs, which is to a large extent due to our modeling technique, which gives the right of way to pedestrians, and they will always use it as well. Another thing that we can see is this trend that is forming for conventional vehicles. So we see that initially travel time will increase and the delays will also increase, but as we move throughout these stages of coexistence, both travel time and delay will decrease. However, we will not reach the same levels of today for conventional vehicles. And lastly, before I move on, I want to talk about the minibuses. So it's obvious that the delay of the minibuses is the largest column in this figure. And as we move on to the prevalent stage, the delay becomes almost as the levels of today. But if we look at the travel time at the same time, we see that the travel time is larger. This is simply an indication that AVs will comply to speed limits, and therefore their delay is not the same, it's not equal as for conventional vehicles, as conventional vehicles try to speed, they tend to drive faster. So knowing that we have these delays in the introductory stage and the established stage, we also implemented a measure to see if we could do anything to reduce the delays, especially of the AVs. And this measure is channelizing pedestrian flows to crossings, and these crossings are here, here, and here. And what you're seeing right here is a pretty extreme case where 5 minibuses pile up, and because they're so cautious, they will simply not be able to drive through. And what happens is that the system breaks down, we have queues that goes out of the network, and traffic demand is not met. So yes, the measure is not it's not recommended. That was for traffic performance, and as Johan mentioned, we also did the safety assessment, which is a qualitative assessment of safety. And we identified that the urban pilot was the driver function relevant for our use case, since it's an urban area. And we also, out of the 79 different accident types that we looked at, we identified 24 of them as relevant for our use case. Most of them, as you can see here, are accident types where pedestrians are involved, which is pretty natural due to the environment that we're investigating. And also a lot of them are accidents with parked vehicles, which tend to happen on Kungstorget, where taxis mainly park for shorter periods of time. So out of these 24 accident types, we've expected to increase safety substantially in 16 of them and moderately in 8 of them. So conclusions, we've seen from our simulations that pedestrians are not affected by AVs. This could of course be debated, but as automation becomes a huge part of everyday life, I think this is also plausible. We see that AVs will be severely delayed by pedestrians until they become so advanced that they are cautious as human drivers. And we've seen that channeling of pedestrian flows causes breakdowns, which confirms the old notion that sharing is caring. So we should keep the shared space as a shared space from this aspect. Also, automation can increase safety of pedestrians, assuming that technology will behave accordingly. And that was all for me.
Thank you, Iman. So the question before, Noreen.
So the next poll, matching with Iman's presentation, is how would you as a pedestrian act in the vicinity of automated minibuses in a shared space area? You can also, in this question, select several options. And the first option obviously is meant to say have full trust in technology, assuming that they will see me. So time's running. I'll give you 20 more seconds to respond to that one. We already have over 40% participation. I close the survey in 5 seconds. 3, 2, 1. And I'll share the results right away. So 60%, quite a lot, say that they would make sure that AVs see them before crossing their paths, so taking the active role of looking out for the AVs instead of trusting. But still, more than 1/3 think then that they can trust the AVs, but still would avoid crossing their paths as much as possible. So back to Iman or Siegfried.
Thank you. We now proceed with another researcher from VTI, Chengxi Liu. Are you ready?
Yes. Yes.
Okay.
Thank you.
Welcome.
Yeah. Good morning and good afternoon. So I'm gonna give a presentation on use case 2. Use case 2 is a macroscopic use case that studies the network impact on traffic flows in the city of Gothenburg. And Gothenburg is the second largest city in Sweden. In the morning rush hour, especially on the motorways, there are always lots of traffics, and congestions are always a problem for the city. In this use case, the research question is to understand how introduction of AV could affect the route choice, travel time saving, and delay, especially under the intensive construction period. And more interestingly, we are also interested in knowing what kind of traffic management measures that can improve traffic performance. So in this particular case, we have looked into 2 different traffic management measures that I will talk about later on in this presentation. Yes, I try to click next slides. Yes. So the baseline model is essentially a traffic assignment model with detailed codings of intersections, as you can see on the right-hand side. Unfortunately, this model doesn't have a demand model, but only a fixed demand matrix, meaning that we could not evaluate impacts on the modal shift in this use case. Actually, in CoExist project, in use case 7 and 8, this will be studied in detail. In terms of the model validity, this model has been calibrated, validated, and been used to evaluate impacts of construction works in many other projects. AV is being introduced into this model using the concept of passenger car units. I think Marcus has a very good presentation about this approach, so I guess I'm gonna quickly pass this slide. Experimental design, we have considered also 3 different uncertainty factors, penetration rates, AV mixtures, and 2 demand configurations, mainly the peak and off-peak. In this figure, you can see that in the introductory stage, we consider the penetration rate varying from 10% to 30% with a majority of basic AVs. And in the established stage, we have AV penetration rate ranging from 30 to 70 with a majority of either basic or intermediate. So we have 2 different mixture types here. In the prevent stage, we have mainly advanced AV with penetration rate 70% to 90%. Yes, and then we present results in a similar fashion as use case 1. And here you can see the relative improvements of different traffic performance indexes. Here we have results for all the vehicles and only for conventional vehicles. And so basically, you can observe a very clear trend that in the introductory stage, AVs have a negative impact on traffic performance, and it turns as long as it reaches established stage with majority of with higher AV penetration rate, you would expect a positive impact. The much larger magnitude of positive impact in the prevent stage, and this is mainly caused by the fact that intermediate and especially advanced AVs they can better make use of the road network capacity. And this is being reflected by the PCO factors, PCO factor values that we have adopted. Also, you might notice that there are large variations in the established stage measured by this uncertainty bar, and this uncertainty bar shows the maximum and minimum values of the improvements of all scenarios that have been tested in this stage. And this is actually not a surprising thing in the established stage. We have more variations in penetration rates and AV mixtures. And here you can see that since modal shift has been not considered and there's not much change in the car kilometers traveled, and this can be considered as major the limitations of this study. Then we have looked into two different measures. The first measure is a redesign of a 3-lane motorway tunnel tube into a 2+2 lane, but reserved only for AV. So by this kind of redesign in the center of the network, we're actually giving more capacities to AVs, but reducing capacities for conventional vehicles. So as a way to prioritize AV when AV share is high. And the results have been presented in this figure. And here you can see that we present results with measure and without measure. So by comparing these two different columns, you can see the impact of this measure in these 3 different stages. And again, you will see a consistent trend that measure 1 in the introductory stage has a negative impact, which is completely logical. Things in the introductory stage, AV share is too low. And in the established and prevalent stages, you can see that measure 1 actually has a positive impact, and therefore measure 1 is being recommended as effective measure. And more interestingly, if you look into the travel time and delays for conventional vehicles, not shown in this figure, you will see there's slightly improvement in established and prevalent stage. And this is mainly caused by the fact that all AVs now start using the tunnel tube on this link, and therefore it freezes capacity on the alternative routes, and therefore conventional vehicle on the alternative routes have much shorter travel time and delay. We then look into measure 2, which is another measure that tries to prioritize AV. So we reserve the bus and AV lane, one bus and AV lane on the major motorway network, as shown on this part of the network. And this part of the network was usually very congested. So by reserving a bus and AV lane, it naturally means that the capacity of conventional vehicles will decrease. But this can be considered also as potential measure if the AV share is high. And the results being presented in a similar fashion as measure 1. And no surprising, you will see that in the introductory stage, measure 2 has a negative impact, but very interestingly, in the established and prevalent stage, we actually do not observe any significant improvements or decrease. So in that sense, measure 2 might not be recommended as effective measure. What's more, if you look at the travel time and delay for buses, sorry, it should be next slide. Yes. Then you will notice that in the established and prevalent stages, bus travel time, the reserved bus and AV lanes will be very congested, especially on this part of the network. Conclusions. So from this use case, we found that AV in general have a negative impact and positive in the introductory stage and positive impact in the established and prevalent stage, which have been found also in some of the previous use cases. And there were large variations in the established stage. Measure 1 in general can be considered as effective measure since traffic performance measure improved in the established and prevalent stages. But for measure 2, it's difficult to motivate this measure as effective measure. Yeah, I think that is for my presentation.
Super, thank you very much. Now again, question time. Wolfgang.
Yeah, okay, hello. Yeah, maybe Jean-Louis, there's a question.
Sorry that I can't hear you for some reason.
No, okay. Can the others hear me?
From my side has some problem.
The rest can hear you, or I at least can hear you, Wolfgang.
Yeah, I don't know, your voice has disappeared.
Okay, then it seems a problem with Jean-Louis' connection. Maybe then a question, here's a general question to all the different demos.
I can't hear anything, sorry. I don't know what happened.
We can write the question in the chat. If you look at we can hear you, and we can write the question in the chat.
I will write the question in the chat to Jean-Louis, but I think we should maybe continue with a more general question. And meanwhile, there's a question to all different demos. If you have made any estimation how the results from Helmond and all the other cities are generalizable, so applied to other locations in Europe. Maybe Johan of Charlotte could maybe answer to this question.
Sorry, I didn't catch you.
There's a question if we have made a comparison from our use cases to other situations in other European cities. So how much is this, our results are generalizable to other sites?
So I think for Jörg can probably tell that when he presents use case 7, but it's similar kind of conclusion as I remember, at least for use case 7 and use case 2. Similar trends for interaction established in parallel. But of course, it's also dependent on the assumptions on these BCU factors based on the simulation results, based on the assumptions of driving logics. Yeah.
Yeah, but given we use the right assumptions or the same assumptions, at least trends are comparable from our results, I would say.
Yeah, from use case 2 and use case 7, that are 2 different cities with 2 different situations, Gothenburg, Stuttgart.
Okay.
Are there any questions from the audience? Any more questions?
No, I think
over 100.
We will add the, I think we will add the question to Cheng-Rui then in the follow-up section in the document. Okay.
Okay. So we just continue. And our next speaker is John Miles from the University of Cambridge. He will be talking about the use case in Milton Keynes. So welcome to John. Can you turn your camera on and your microphone?
Can you hear me now?
Yes, we can hear you.
I'm sorry. Okay,
Super.
then good afternoon, and thank you, Siegfried. I can't yet see my first slide, but I hope it will come up any moment.
Wolfram, please.
I've got it now, thank you. Then thank you very much, and I want to present the results from the UK for use cases 5 and 6. My slides don't seem to be transitioning, so I'm just going to use the marker here. Yes, and so our agenda is that I'd like to begin just by introducing the background to the simulations, talk a little bit about the traffic modeling background particularly, and then go into use case 5 and use case 6. Use case 5 is a big simulation, city scale, and use case 6 is a subsection of the city looking particularly at an arterial road with intersections, and in the city of Milton Keynes, those intersections are usually roundabouts. Milton Keynes is not a typical city in the UK. It is a planned city, and it was built from a greenfield site starting about 40 years ago, and it has been developing ever since. As a result, the layout is very regular. It's a network grid. And you can see from the map on the screen now that it's a very regular grid. This makes it not typical of many UK cities, but it is reasonably typical of lots of suburban areas in the UK. So a lot of the lessons that we think we've learned in CoExist should be transportable to the suburbs of other cities. The city has been very successful economically, and it is expected that it will grow to maybe double its size in the next 15 to 20 years. And so there is considerable concern amongst the authorities about the traffic implications. And so our work in CoExist has been to look at the future traffic implications, given that there will be an expanding network of vehicles running on the roads, and some of those vehicles may become autonomous. Our simulation is citywide. What we're interested in is how do the overall city network, city flow patterns change as we get increasing shares of connected and autonomous vehicles on the road. So an important characteristic of our studies is that they are a very large scale simulation of the whole city, in the first case for use case 5, not of just a part of the city. Coupled with that, we are looking at very high levels of traffic density. So we're interested in the peak time flows in the morning and the evening. So our simulations are oriented towards traffic levels which are close to the capacity of the roads as they are currently defined. So traffic densities are high, the model is large, and then just a few words about the various different scenarios that we're looking at. First of all, our introductory stage, where we assume this is in the relatively near future. 80% of our vehicles are still conventional vehicles, and only 20% are autonomous vehicles. And of that 20%, 16 fall into the cautious category and 4 into the normal category. Our established stage assumes that 50% of our vehicles now are conventional, so that percentage is dropping. And you can see the percentages of the other vehicle types on that column, which has just appeared, split now between cautious CAVs, normal CAVs, and even a few of the very capable all-knowing CAVs. And our final distribution is 30% of conventional vehicles, and then 14 and 56% of normal and then all-knowing vehicles, as you can see is shown there. Just to remind you, the differences between these cautious, normal and all-knowing CAVs is essentially in the distances which they leave between vehicles. The cautious CAVs leave big distances and smaller as we go up the capability level, and also the variability of those distances. CAVs will have much tighter control of the distances between vehicles, much closer to specification than a normal human driver that varies quite a lot. So these are the factors that will lead to the differences in performance between our various different scenarios. So coming on now to talk about use case 5 specifically. The exam question for use case 5 is a very practical one. It is a question posed by the city authorities, and the question is, what would be the citywide traffic consequences for Milton Keynes if CAVs become commonplace and the city centre is redefined as a car-free space? So we are asking two questions in one here, because there's a great interest in releasing car parking space in the city centre so that it can be built into more commercial and retail space. So introducing car-free space in the city centre is a pretty big question, and the influence which the arrival of CAVs might have is an important aspect of that question. So here is our VISIM model. It's a micro simulation of a very large part of the total city. It has led to us having very long run times because we have this big model with many intersections, and we also have high levels of traffic density. And our first simulation was a baseline simulation. It was simply to introduce various different penetration levels of autonomous vehicle without there being any change to the city centre traffic. So our first baseline study was no measures introduced in the city centre. We still have cars in the city centre, simply what happens to the travel times and the delay times when we introduce these different mixes of autonomous vehicle. And you can see there that the introduction of cautious vehicles during the introductory stage really makes the traffic flows significantly worse. The travel times increase and the delay times increase, very significantly. By the time we get to the established stage, where we have a much bigger degree of second generation CAVs in the mix, then those differences are being reduced. And indeed, by the time we get to the third stage, where we now have quite a high degree of advanced CAVs in the mix, the so-called all-knowing vehicles, then we're getting significant advantages. And this is quite an important point. The delay time improvements on the right-hand side there, when we get to the prevalent stage, are really quite significant. We're getting 10% improvement to delay times across the whole city, and it might cost many millions of pounds to get that sort of improvement by junction modifications to the infrastructure. So I think this is quite an encouraging result. We then go on to introduce the car-free element in the city centre, and we did this in our model by essentially taking out the zone within the blue box that is shown there and not allowing cars now to move inside that box, but rather at the perimeter of that box they would be intercepted and people would get out of their cars and then walk around the city centre. And what we were looking at in use case 5 were a series of interventions where we have different types of intercept at the points where the yellow dots indicate the interception. So the autonomous vehicle comes to one of the 6 yellow spots, drops the passengers off. The passengers proceed on foot or by some other form of autonomous transport within the city centre, and the car goes away again or is parked up. And what we're most interested in is what does that do to the roads that are just on the perimeter of the city centre, because you can imagine as the autonomous cars come into the edge of the city centre, stop at the yellow spots, drop the passengers off, they could cause a lot of congestion in the adjacent roads around the city centre. So our real interest is focused on those roads within that yellow band that is shown there between the perimeter of the road network and the city centre zone. So our measure 1, the first of our interventions in the city centre area, was to put what we call pick and drop areas. This is where the car comes into a parking space, drops the passenger and then moves off again, goes back into the city to pick up other people. From other calculations we did, we estimated we would only need 5 of these, not necessarily 6. And so our use case 5 with measure 1 modified our network to look like this. And you can see there that the pick and drop zones are put at 5 locations. Each of the pick and drop zones is a specially designed area which has some 14 lanes where cars can come in parallel, drop passengers off and then take off again. So this is really quite an efficient means of dropping people off and picking them up. And we can see from this that if we were to introduce a system like that with the first generation vehicles, cautious vehicles, then we would actually get significant delay time increases for a journey to the city centre during peak time. But that would rapidly get better when we move to the established stage with normal vehicles, the prevalence of normal vehicles, and indeed the prevalent stage when we get on to having all-knowing vehicles. So generally speaking, this would be a good result. We then looked at measure 2, which was rather than having the so-called pick and drops that I've just explained, where we drop a passenger off and the vehicle flies away quickly, now we have a series of multi-storey car parks at the entrance points to the city centre on the perimeter. As you can see, the 6 yellow dots. Now we do need 6 facilities, and we get a different set of results. And these are generally quite significantly worse than the pick and drops. And that is simply because the car parks have much more congested entry points. And what we see happening in our model is that the car park entrances begin to block up and we get tailbacks of traffic onto the main city roads. I've lost my... we get tailback of traffic like this, which go from the car park entrances back out onto the main city roads. And they clog them up. So our measure 3 is to introduce an additional lane on the adjacent roads. And that has a significant beneficial effect and indeed brings the car parks back now to being marginally better than the pick and drops. So putting in an additional lane on the boundary roads is a very beneficial thing to do. So if we summarize all of our results now, you can see on the left-hand side our baseline case where we still allow vehicles into the city centre, but we now progressively introduce cabs. That's our baseline case on the left, no measures. When we introduce the pick and drop, then things get better. When we introduce car parks, they actually get a bit worse again. But if we introduce car parks and additional lanes, then we get better again. So it would seem that if we begin to get cabs coming into our city centre, and if we simultaneously want to introduce a car-free zone in the city centre, then that is a combination that could work quite well, albeit that in the early stages when we only have cautious calves, there would be a degradation. By the time we get through to the second and third stage of calf introduction for normal and all-knowing vehicles, then things are getting better. And our qualitative assessment of the situation both in the urban centre and also the arterial roads out in the more suburban parts of the city, generally speaking, we anticipate that there would be a significant improvement in safety for all the variations that we have been looking at. Coming on to our use case 6, I did say earlier that Milton Keynes is dominated by its grid layout with roundabouts at each intersection, and you can see a typical roundabout here. And our question here is, what is the effect of traffic flows at these unsignalised intersections, the roundabouts, for various different stages of CAV take-up? Our model, I just jumped over that slide a bit too quickly, I'm sorry. Our model is a short section of arterial road with 3 intersections on it, and the results we get when we have no physical measures introduced, simply introduce CAVs, follow the trends we've seen before. When we have the cautious CAVs, things are worse. When we get to the position for the established stage, where we're dominated by normal calves, things are about the same as traditionally. And when we get to all-knowing calves, then things get significantly better. We then looked at a couple of physical measures that could be introduced. Measure 1 was to introduce car-to-car communications, either directly or via some form of communications tower mounted on the centre of the roundabout. And the results that we see from that is that, first of all, it greatly magnifies the delay when we have cautious vehicles. That's simply because the cautious vehicles are talking to each other and they're slowing down each other and they're slowing down the traffic around them. As we move to the established and prevalent stages, that quickly goes away and we get improvements across the roundabout. Our measure 2 is to take advantage of what we see as potentially very important benefit, which is if you look at this road with its 2 lanes of congestion, in future, if we have autonomous vehicles, we could have much tighter lateral controls. And if we had tighter lateral control, we could get a 3rd lane in where we only have 2 lanes of traffic at the moment. So our simulation introduced a 3rd lane, and instantly we see improvements across the board, even when we have cautious vehicles on the road. So that's a very promising result, but of course it's not very easily delivered, because you can't introduce a 3rd lane safely until all of the vehicles are autonomous. And even in our prevalent stage, as you can see here, we still have 30% of conventional vehicles. So this introduction of a 3rd lane gives us 50% increase in capacity instantly, but it's not really very easily delivered until the penetration levels of calves get right up high to the 100% mark. Our qualitative safety assessments, again, all very positive. And so I'd like to leave you with some poll questions which really have to do with what level of cautious calf penetration might be required for the collective effect to be noticeable on these macroscopic traffic flows. Now, it's not necessarily noticeable for the better, but just for them to be noticeable.
So you can click on the screen now. And you have 20 seconds to submit your answer, please. Five seconds left for everyone. We already have reached almost 60% participation, which I find really good, especially given the time that we've been listening, watching, talking today already. And I'll close the poll in 3, 2, 1. And I'll share the results right away. So maybe, John, you can also have a look and let us know what you think about it. So yeah, 1/3 say that 25% would be required. 50 or 75% are considered less likely or less probable, and 24% of participants say that 15% should be required.
Yes, I would say it's a very interesting result and reflects my own views, because with cautious calves, they travel really quite slowly and very carefully compared to conventional vehicles. So they begin to have an effect at really quite low penetration levels. So 15 to 25% would be my view, that we'll see the effects from those low levels with cautious vehicles. Our next poll is a similar question, but for more advanced vehicles.
So same question, only for all-knowing calves, CAVs. Please answer now. You'll have 20 seconds again to answer. And we've already almost reached 30% participation, so keep doing it, keep answering. And I'll close the poll in 3, 2, 1. Share the results again. Well, more or less similar, even though, I mean, more than 40% of participants say that 50% penetration should be required for this type of CAVs, and higher percentages also expecting even 75%. So yeah, there are a few differences.
Yes, thank you.
What do you say, John?
Well, again, I'm really impressed by the audience, because that again reflects my view, which is that the all-knowing vehicles, which can travel relatively fast, have less effect collectively on the general traffic flows until they get to higher percentages, rather than the less capable calves, which tend to slow everything down because of their caution. Thank you.
Thank you, Tree.
So,
okay,
very good.
it's time again for questions. Yeah, thank you. There are 2 questions, John, which go maybe more or less in the same direction for use case 1. Have you considered empty cruise impact for pick and drop scenarios?
That is embedded in the calculation, because we include the vehicle leaving the pick and drop and going off back out to the suburbs again, yes.
So going out to pick up new passengers.
To pick up another passenger, yes. They're going out empty to pick up another new passenger.
Okay, thank you. Then maybe another question. It seems that a rather small amount of CAVs have rather big impact on microscopic scale. So, and the polls also show this. Do you have have you done any quantitative studies looking at the citywide traffic versus effects versus the CAV penetration rates?
Yes, we have. In another project, and to a certain extent in this project, we have looked at the question, you know, how many calves, what penetration level of calves do you need to have before you start seeing marked impacts? So we have done some work on that, and it is surprisingly quite low percentages. We can see quite significant effects building up below 50% penetration. And I think that's not intuitive. I think a lot of people think you won't see any effects until you get to 80 or 90% penetration. But the studies that we've done show that the effects, both beneficial and also disadvantaged effects, both of those effects show up at much lower penetrations, maybe 25, 30%, 40%.
Thank you. Could you maybe forward us the links to these studies that we could then include these into the follow-up
yes, I'd be
documentation?
Happy to do that. Yes.
Okay. Thank you very much. Over to you again, Siegfried.
So time is running, and we have one final presentation. So back to Stuttgart again, Jörg Sonnleitner, Research Assistant at the University of Stuttgart. Please give us your report about Stuttgart.
Yes, thank you, Siegfried. So let's start with use case 7, which is about the impacts of CAV on travel time and mode choice on network level. Those impacts are caused by changes in supply, where road capacity and traffic performance are influenced by CAV. And on the other hand, they are caused by changes in demand, where people may perceive the travel time in automated cars differently. We expect that we will get effects on, again, both supply and demand. For example, changes in travel times, mode choice, and destination and route choice. And the question now is, to what extent will we see such changes? Both Stuttgart use cases run a macroscopic travel demand model, which covers 2.7 million inhabitants of the Stuttgart region. The model covers the trips of an average working day and includes all expected measures by the year 2025. The available modes of transport are car driver, car passenger, public transport, and the active modes bike and walk. Our basic assumption on the supply side is that CAV perform differently than conventional vehicles, and therefore we decided to use the concept of passenger car units, where every vehicle is converted into this standardized unit of passenger cars. Additionally, we extended this concept for CAV to be additionally dependent on the road type they are driving at, because we think that the behavior of CAV will be different on different road types. Evaluating PTV's microscopic traffic flow simulations data resulted in this table, which serves as input for the model runs. So the lowest level of roads, feeder roads, there travelers have to drive manually, as well as for the basic CAV on urban streets. The basic CAV performs worse than CV, which is reflected by PCU values greater than 1. The intermediate CAV starts to perform better on some road types, and the advanced CAV performs better than CV on all road types where it's possible to operate automated. For reasons of simplicity, I will refer to arterials and urban streets as main roads in the following slides. On the demand side, we have to talk about the perception of travel time. So imagine you sit in an automated car and it's operating in automated mode. This means you don't have to drive manually, and you will probably perceive the travel time differently because you are free to read a book, write mails or messages, or maybe even watch a CoExist webinar. And we think that this needs to be included in the model. And now it's important to stress that use case 7 considers highly automated vehicles and not fully automated ones. And these are just a transport system, which is part of the mode car driver. And therefore it influences the attractiveness of this mode. We applied 3 assumptions regarding the perception of travel time: no changes, or travel time in automated mode reduced by 15 or 30%. All different assumptions, we can see how the scenarios are designed. So first we need existence, free, introductory, established, or prevalent. And in each of them, we also need a CAV share. There we varied between 20 and 100%. As just explained, perception of travel time. And we also need to define a road network which is CAV ready, so their CAV are able and allowed to drive automated. One case is where we have a road network consisting of motorways and motorway similar roads to be CAV ready. And the second state is where additionally main roads are considered to be CAV ready. And now we can combine all of those assumptions and each of the combinations corresponds to one scenario. We almost conducted all possible scenarios, and we'll now have a look at selected results. We see the total distance traveled for the base case. The table below indicates the assumptions for each scenario, and all values are normalized to the baseline, so we can compare them easily to the base case. And if we now introduce another scenario with CAV, for example, in the introductory stage with 40% of CAV, no changes in perception, and the motorway network to be CAV ready, we see that we have some changes of the total distance traveled, -1%, and also changes for the share of car driver. This share also corresponds to the vehicle distance traveled. Why is this the case? So introductory stage, CAV perform worse than CV, and therefore we will have small modal shifts from the car modes towards public transport.
Hi, Jörg.
The distance
Can you hear us?
goes down.
Jörg, you're having network problems.
Scenario is 60% of the assumptions as before, and now the impacts turn into the opposite direction. Modal shifts from transport towards. Sorry.
Okay. You're having network problems. I don't think we can do anything about it.
Can you hear me not well, or?
No, there are gaps.
Should we turn off the cameras? Maybe it's going to work then.
Should I just proceed?
Suggestion?
Turn off the camera. I will turn you off. Yes. Okay, you can
Is it now
continue.
better?
Yeah, just continue.
All right. I hope you can hear me well. So
much better now. Thank you.
If we look at a scenario in the established stage with 60% of CAV and the same assumptions as just before, results turn into the opposite direction. Now CAV perform better than CV, and we will see some modal shifts from public transport to the car modes. If we now additionally consider changes in the perception of travel time, we observe that the trend intensifies. So we will have a larger share for trips for car modes as well as for the distance traveled, and also in total. So now people start to choose other destinations, do longer trips, travel further. And if we now look at another scenario where we extend the CAV ready network to include also main roads, the numbers go even up again, because now car users benefit on more parts of the network from the advantages of CAV. And if we now look at some scenarios of the prevalence stage with a penetration rate of 80% and the same assumptions as for the established scenarios, we can observe the same trends, but to a greater extent. So the higher CAV share and the better performance of the advanced CAV result in bigger changes. So we will have around 12% an increase in total distance traveled and up to almost 20% of vehicle distance traveled. To conclude for use case 7, the model results indicate that highly automated vehicles may have a substantial impact on travel demand. And in the long term, total distance traveled will increase. Why is that the case? The reason is that CAV perform better than CV, and the car modes are becoming more attractive. people will switch from public transport towards the car modes, and with the benefits of perception, also the destination choice will change and people will travel further. In the end, we will have more and longer car trips, so total time spent and distance traveled increases. And these rebound effects on travel demand may reduce the positive impacts of CAV on capacity and traffic performance. So I will proceed with use case 8. This use case is the second Stuttgart use case and the last use case of all. And it is about impacts of driverless car and ride-sharing services, where we look into the effects of driverless mobility services like car or ride-sharing. Again, we expect to see some impacts on supply and demand, for example, on mode choice, travel times. We wonder about the required fleet, which is necessary to serve the demand. How many empty trips will we get, and what will happen with the vehicle distance traveled. Use case 8 uses the same macroscopic model as use case 7, but it is extended by necessary methods and algorithms to enable the model to include these mobility services with everything that goes with them. We decided to examine 6 cases, 0 to 5, and these cases differ regarding the available transport modes. What modes do we have in general besides bike and walk? On the side of car transport, we will have something we call no sharing. So this is basically just a private car. We will have car sharing, which you can imagine as a ride-hailing service as Uber, and ride-sharing, RS-, where trips are also pooled together. So it might be that you will share parts of your ride with strangers. On the side of public transport, besides the traditional public transport services, bus and rail, we can also think about a ride-sharing service, RS+, which is fully integrated into public transport. This means that it can serve as a first or last mile service and add up to the traditional public transport. But for trip requests where public transport service quality is insufficient, it can also be that direct trips are offered to the travelers. And now case 0 is our base case. So we have the traditional public transport and private car. And the first indicator we will have a look on is the vehicle distance traveled for private cars. Now we can see 2 columns, 0% and 50%, and this states the share of persons that are willing to give up their private car, to give up their ownership. And these arrows indicate the trends in comparison to the base case and 0%. So here we have naturally no changes. And if half of the people give up the private car, vehicle distance traveled will go down for private cars. The same indicator for all cars now includes also the vehicle distance from commercial and external trips. And for the cases 1 to 5, it also includes the vehicle distance for the sharing vehicles. And we will also look at the number of vehicles required. Also, of course, for 0%, no change, but if half of the people give up their car, it will go down strongly. Now, case 1 and 2 each introduce one additional transport mode, car sharing or ride sharing, which is competing to public transport. And we see that both cases have show very similar results, show the same trends. The main difference now to the base case is that the vehicle distance traveled for all cars goes up, this is the case because we have modal shift from public transport towards these new sharing modes. Cases 3 to 5 now consider the ride-sharing service which is integrated into public transport, and these cases differ regarding available bus service or if an additional car sharing is possible. And those 3 cases also show similar results. And together with this ride-sharing service, public transport is now quite convenient and comfortable to use, so it will attract a relevant share, modal share, and so people will also switch from private cars and from traditional public transport towards this new public transport service, RS Plus. So we will also have an increase in vehicle distance traveled for all cars, although the vehicle distance traveled for private cars goes down. And if half of the people decide to give up their car, those indicators will show even a stronger decrease. We can state that the assumptions on willingness to give up the private car ownership and the price levels of these mobility services play a crucial role and have a large impact on results in general. With car ownership as today and out-of-pocket costs for sharing systems which are 50% higher than the costs of private cars, these services will only attract a relatively small amount of trips. And another general conclusion, situation today, parking prices and the congestion limit the car demand in cities, but in the future, ride-hailing services eliminate these parking costs and therefore increase car demand, especially in cities more than in rural areas. Thank you very much for your attention.
Thank you very much, Jörg. So to conclude your session, I would like to launch another poll that matches your presentation. So to the audience that's still here, well done. And the question would be, how and where should automation first be deployed to rip the most? So this is only one choice each. And yeah, please let us know what you think. People are already voting. We have reached 20% participation, and I'll give you 20 seconds to submit your answers. Okay. 5 seconds left. I count down 3, 2, 1 and close the survey. And I'll share the results here. So most people think that automation should start with road-based public transport, so buses and shuttles, 70% of participants, and then a huge difference down to 20% of participants think that ride sharing such as Uber or ride hailing, vehicle sharing, Car2Go should be the first to deploy automation. Thank you very much, everyone, and thank you, Jörg. Maybe you have an opinion about that as well.
I like the result because the question did not ask most benefits for whom, for the individual traveler, for the city, but obviously most of the attendants like the idea that public transport should be strengthened, and I think a better public transport is always good for any city, so I hope that the majority is right here.
Cool. Thank you, everyone.
So we still have close to 90 people participating. Wolfgang, is there a question still? Are people too tired to ask questions?
No. People still ask questions. maybe two of them. One for a more clarification question, Jörg. How many seats does a shared vehicle have in your model?
We decided to have 6 seats in a shared vehicle, but as Markus Friedrich explained earlier, we adapt this capacity of the vehicles to non-integer demand. So if, for example, the first trip request is made from 0.7 persons, then the vehicle will have 0.7 times 6 seats capacity.
Okay, thank you. Then maybe one final question related to use case 8. How did you include car sharing and ride sharing in your mode choice model?
Well, that's I'm not sure if it's I'm able to answer this in one sentence, but in general, we have a loop in travel demand modeling procedure, and we calculate the quality of these services and have these this split in 96 intervals with 15 minutes. And so in the end, you will get a lot of matrices that are aggregated and fed back into mode choice. I hope this clarifies it a bit.
Okay, thank you very much. I see one raised hand, Siegfried. Maybe we tried last time.
Yes. Can you introduce yourself, please? Charlene Srivastava, I'm opening your mic.
Yeah, hi. My one observation and you can say comment is in the demand modeling. I found that one of the very important element about the cost is may be considered but may not be explicitly mentioned in the presentation. So I was wondering about how the cost and with different level of automation is also change of type of fuel as well. It may not be fossil fuel, it may be more electric when we are talking about 2035 or 2045 in line with various policies by various federal governments around the world. So just a comment or observation that these two elements, because cabs will not be cheaper than what current cars are, and if they are electrified, they will have issues with the charging and infrastructure related to it.
Okay.
Yes, thanks
you.
for
Thank
the question. So time was short, so I did not mention all assumptions, but the sharing systems that are operating independently to public transport, so competing with public transport, are the most expensive ones. They have prices as well, fixed price for booking, as well as a distance-based fee additionally, and they are around 50% higher than the out-of-pocket costs for private vehicles. The ride-sharing service, which is integrated into public transport, is cheaper than the independent ride-sharing service. So if you use it as a first or last mile service, the costs are included in the public transport ticket. If you use it as a direct service, then you will have to pay the average price calculated from public transport per kilometer.
Okay,
and
thank you very much.
We have not considered anything about charging whatsoever.
Okay, thank you very much, Jörg. We will also write down this answer in our follow-up documentation. As was mentioned several times today, you will get some follow-up emails with the slides, with the recording, and also with answers to all the questions which we could not answer today during the course of the webinar. I think we should come to an end. So maybe, Wolfram, if you just continue with the one slide where I just summarized some lessons learned, please. Okay, thank you very much. yeah, I think hopefully we could show today that we have developed in CoExist some tools which really help to make decisions toward cooperative and connected automated mobility scenarios. So we hope that we get from a gut feeling to a more structured and informed decision making. But of course, I think all the presentations make this clear. It's everything about what are your assumptions, and in the future, I think also how do you communicate your assumptions to decision makers so that they really understand the impact of the scenarios. We have developed some assessment tools also for these scenarios, but actually this is also a trend for all use cases. You could see that in all the use cases, the mobility improvements mainly only come up for high automation and penetration levels. So say a bit more bluntly is maybe we all have maybe to face a health scenario before a heaven scenario. And this is actually also a focus of the CoExist project, that we have really do more research on this upcoming transition phase when we have a coexistence of conventional and also automated vehicles. Throughout the project, we had a lot of contact, of course, with our use case cities. And it was a lot also about cities expectation management. When we started CoExist, the hype and expectations were much more positive, I would say, than as it is now. There's more a sober assessment, I would say, regarding the impact of automated vehicles. And it's mainly lessons learned from the cities around how to prepare for planning for CCAM. And this is actually maybe also already a teaser for the webinar tomorrow, where we focus really on the automation readiness of cities and how they prepare really for planning for this, which will start tomorrow at 2 o'clock. And I hope, of course, that a lot of you will again join us. I think in the end, Siegfried asked at the beginning, what are your expectations? And there was one short comment to learn about the CoExist project results. And I hope we did with this webinar today, show you what we developed in terms of automation ready modeling and also assessment planning frameworks to reduce uncertainties to plan for connected cooperative automated mobility. And that's it from my side. So Siegfried, please take over, and I think you will end then the session.
Really just one more minute, everybody. Thank you so much for participating for such a long period of time. We still have over 80 participants after more than 3 hours, so this is really great. Wolfgang has said what will happen tomorrow. Please remember, it is a different link. You can still register on the CoExist website, but it is a different link for the meeting tomorrow. Then just very quickly, Wolfgang, can you advance the slide, please, for me? Very quickly, there is another webinar coming up. Please go to the CoExist website for that too. And then finally, Wolfgang, please. Even more recorded webinars, also the one that was mentioned by Charlotte today from PDV, and other information. And finally, thank you to the project partners. This was really great. You have invited us to your homes, so thank you for that. And I look forward to seeing you tomorrow. And if there is a question, here are the emails and other details. So thank you, and hope to see you soon tomorrow at 2 o'clock. Bye-bye.
Thank you.
Bye, thank you.